Okay, in this video we're going to talk about the extra practice problems from Chapter 12, and this has to do with our fluid dynamics, or fluids in motion. Example 12, number 1, said that we have a garden hose with an inner radius of 0.015 meters. They told us that it was 1.5 centimeters, so I've already made that conversion. And it's feeding a 30 spout sprinkler, so a sprinkler that ends up having 1.5 millimeters of radius. And if we convert that to meters, that's 0.0015 meters. And we'll note that we have 30 of those, so 30 of those 1.5 millimeter sprinkler outlets. The water meter measures a flow 9.5 cubic meters per second, which is supplied to the garden hose. 9.5 times 10 to the negative fourth meters cubed per second. Okay, so our question is to find the flow speed of the water through the hose and the speed of the water exiting the sprinkler spouts. Well, two things to remember. Volumetric flow is equal to some amount of volume that passes a point in a certain amount of time. And with some extensions, we found that that's equal to the cross-sectional area times the average velocity. Now, this is a capital V for volume. This is a lowercase v for velocity. Either one of those definitions work. I'm using the cross-sectional area times velocity definition here because we're going for velocity. We're trying to solve for velocity. I'm also going to assume that this hose is circular. So when we take the flow rate Q and divide it by the cross-sectional area, which is a circle, and sub in the numbers, all of our units should work out nicely to leave us with 1.34 meters per second of flow. In part B, same thing, except this time our flow rate must be equal to 30 of these spouts with a cross-sectional area times velocity. When we isolate velocity this time, we'll take our flow rate and divide it by 30A, and in this case we end up seeing that the velocity is 4.5 meters per second. So it's good to see that the flow will increase. I think that makes sense. We have a large garden hose and the water's moving through at one particular speed, but as it exits through the sprinkler nozzles, then we see that the velocity has increased. Now, there was a second video that I had posted for this week. It was the crash course. Sorry about that. It was the crash course on YouTube from PBS Video on fluid dynamics, which was the number 15, I think, in that series. I think they ended up calling it Fluids in Motion. From that video, towards the end, they start talking about Torricelli's law, and that's the law that states, well, if we've got a vessel filled with water and we put a spout towards the bottom, the pressure associated with the weight or mass of the water being accelerated downward is going to generate some outward speed of flow, and we can determine the velocity of that flow where it goes, but an interesting byproduct of that is that if we turn this spout and angled it upwards, that the water flow as it sprays upward will only reach a height at which the water level exists at that moment of time. So as more water falls, then the pressure is only sufficient to push it up to the height of that water level. So that's the background information that you need to know for this particular question, and that Torricelli's theorem states that the velocity of the water flow is equal to the square root of 2 times gravitational constant times height. And then when we start substituting that information in for flow rate, which is equal to cross-sectional area times velocity, well, we now know our velocity. We can obtain the cross-sectional area from this particular word problem. And then finally subbing in the height at which the water fountain is spraying its water. We've got all the components necessary to determine flow rate, and flow rate, of course, is measured in cubic meters per second. Now, the problem does ask us to find what this flow rate is in gallons per minute, so we just need a simple conversion there. We can convert our seconds into minutes by multiplying by 60, and then we can convert from cubic meters into gallons by dividing by 3.79 times 10 to the third. Another option here, though, is instead of dividing by this small decimal, in class we recognized that there are about 264 gallons per 1 cubic meter, so we could have multiplied by 264 as well. And in either case, we obtain a result of about 78.4 gallons per minute. So I hope that helps with the extra practice problems from Chapter 12. Again, Chapter 12, we only spent a little bit of time studying it and only a couple sections out of the entire chapter. And this should be sufficient for you to practice. And we can talk more about it next week when we do our final review. Thanks for watching.